What if I told you you can fine-tune the brand new Llama 3.1 model released by Meta and deploy it on your own infrastructure for blazing fast inference speeds using NVIDIA NIMs all directly from your laptop? Hi, I'm Carter Abdallah. I'm an engineer on the dev tech team at NVIDIA working on the BrevDev platform, and today we'll be leveraging tools like NVIDIA's Nemo Framework, NVIDIA NIMs, and BrevDev platform to accomplish all of those things. So we're going to start off looking at build.nvidia.com. This is a playground, essentially, where you can play around with APIs for a lot of the models. Today, we're talking about Llama 3.1, 8B Instruct. Of course, there's the 70B and 405B versions as well. And you can see code to execute this if you wanted to put this in your own application. But again, these are APIs hosted by NVIDIA. So we can, for example, ask Llama 3 about a limerick about the wonders of GPU computing, and we'll see what the responses are from the Llama 3.1 8B Instruct model. But what if you wanted to fine tune this? You wanted to teach Llama 3.1 about your own particular use case. Today, we'll be doing essentially an example as if you were a law firm and you had a bunch of data that you wanted to trade it on. And in that case, you need to be able to actually fine tune the model, and then you want to deploy it. So what you're going to do is you're going to click build with this NIM, and we're actually going to go through and join the NVIDIA Developer program. As you can see, if you use a personal email, you can actually self-host NIMs on your own infrastructure. So I'm going to put in my own personal email here and sign up for the developer program. So now that I've created my account, I'm just going to give my cloud account a name. And then it'll ask me to join the developer program. So once I join the developer program for the self-hosted API, I'm going to put in my name here and say that I'm a developer because I want to fine tune it for my own use case. I will get an NVIDIA NGC API key. So this API key, you want to save it so that you can pull and run the NIM locally. So you're going to copy this, and we will use it later in the tutorial to actually pull the NVIDIA NIM for the Llama 3.1 8B Instruct NIM. Now that we've joined the NVIDIA Developer program, we can pull the NIM using that key we just generated onto our own machines and swap in LoRAs, for example, which we'll be creating today, which is a fine-tuned version of the Llama 3.1 8B model. So if you follow the link below in the description, this is a BrevDev Launchable. A Launchable essentially encapsulates some kind of compute that we will provision for you, a container, in this case it's a Nemo container, so that we can actually fine tune using the Nemo framework, and then a notebook associated, which we can actually read here. So if you follow the link below, it should take you exactly to where I am now. You will have to create a BrevDev account, and then all you have to do is click Deploy Launchable. And so we will actually be putting this notebook onto the A100 machine that is in GCP that we're provisioning for you. Today, what we'll be doing is actually fine-tuning Llama 3.1 8B Instruct using LoRA, which is low rank adaptation, which I'll explain a little bit later, using the Nemo framework. And we'll be fine-tuning it on a specific use case. So imagine that you are a law firm, and we'll be using the Law Stack Exchange dataset, which is essentially a forum where people would have questions and answers related to law-related questions. And so imagine you wanted an agent or something to be able to answer questions from the data that you have in that forum. So we'll be using this data set and training the Llama 3.1 model to do a very specific use case. Today, what we'll be doing is from a given question, try and predict the title for that question. So you can imagine, let's say you have a forum worth of, car salesman data, or not even just a forum. You have a specific data set that you want to be able to fine tune a model on so that it gets really good at your use case. If you think about the model off the shelf, it's really good at a lot of different things, but a model becomes a lot more powerful when you train it for your specific use case, which is why it becomes so valuable to be able to not only fine tune it, but also host the model yourself. And NVIDIA NIMs, which is NVIDIA NIM Inference Microservices, is really powerful for inference speeds, blazing fast inference speeds. So phase one of this notebook will be fine-tuning the LoRA adapter based on that data set. Step 2 will be actually running the fine-tuning script. Step 3 will be performing some inference to see how good our model does, but we'll be using inference with Nemo framework. But then step 4 will actually be deploying it on the NVIDIA NIM, which we just got access to by joining the NVIDIA Developer program. Right now, as you can see, our GPU is already deployed. So if I go to the instance page, we can see that our GPU, which is the A100 80 gig, you need the 80 gig in order to get the 8.1 billion parameters to fit on the GPU. And we have the Nemo container that's actually building. And so at any point, you can come to your instances page on brev.dev and see us see what we're doing on the machine. Right now, we're essentially building that Nemo container. And once it's ready, we'll be able to open up this notebook that we were just viewing. We'll be able to open that on the machine. So we will actually be able to perform all the fine tuning on the very powerful A100, but you never have to leave your browser. Once the container is done building, I'll get back to you guys and we'll actually open the notebook and we'll be able to begin the tutorial. Alrighty, as you can see, now building our container is done. We drop a little shaka in the logs there to let you know that your container is ready. We see built here, and this open notebook button is now glowing. So all we have to do is click that. And now what we'll actually be doing is we'll see the same notebook that we just saw on the page before, but now we're running it on the very powerful A100 GPU. And so we have the same notebook here, and we can actually just start walking through and running the steps. The first step here is you can press Shift Enter to go through the cells and actually run them. The first setup here is downloading the Nemo checkpoint file for the Llama 3.1 8B Instruct model. This will take some time because obviously there are 8 billion parameters as part of it. And if you're unfamiliar with Nemo, it's just their file, the .nemo is just their checkpoint file structure, essentially, to have you be able to run, different types of fine tuning processes. And Nemo in general, if you are not familiar, is a scalable and cloud native generative AI framework. But basically, it's a suite of software tools that will help you with every step of the AI ML dev lifecycle. Everything from data generation, data curation, actually changing the data into a format that's necessary for your particular use case, fine tuning. In this case, we'll be using LoRA PEFT fine tuning, which I'll explain in a bit, all the way through inference, and then even deploying on stuff like NIMs. And an NVIDIA NIM is essentially a hyper optimized container for inference to where it will actually be hyper optimized down to the hardware level of the GPU you're running on. So we will be running the Llama 3.1 8B Instruct model that we've fine-tuned, and it will be hyper optimized for the A100 80 gig GPU, which we will be running today. And it will give you essentially the fastest inference speeds possible. So NIMs are becoming increasingly popular, even in enterprise, to deploy at scale and to have really, really fast inference speeds. And so as part of the developer program, now you have access to start building on top of NIMs as well. So right now we're just downloading the checkpoint file, and I will, whenever there's a step that'll take a couple minutes, I will skip ahead to when that step is done. As you can see, the cell here has a little asterisk next to it. Once that turns into a number, that means that the cell is done running, and I will get back to you then. Alrighty, as you can see, it's done, and we can just run ls to see that we actually have the file here. We see it on the left. It's the directory with the necessary checkpoint files. Now we're just going to import some necessary software libraries. And the next thing we need to do is we actually need to prepare the data set for the fine tuning. Llama 3 expects a particular type of data set, and we want to prepare it so that we can actually use LoRA, which is low rank adaptation, which I'll explain in a moment. As I mentioned before, it's a subset of the Stack Exchange data set. If you want to see what the data set looks like, you can click here, but there's actually already been some filtering done to make sure that the data set we're using to fine tune is actually going to be really effective in that use case. If you're more curious about, for example, data generation or the pre-processing, then you can refer to this data generation notebook. I will not be going through that as part of this tutorial, but data is a huge part of fine tuning and in general machine learning. And so this involves a little bit of information on how you might be able to even create synthetic data that you could train your model upon. So we're going to download the data set that is, again, already pre-processed and filtered from this Stack Exchange data set. We're going to unzip it, create the data directory, and split them up into training data sets, validation data sets, and test data sets. This is very common. And now what we're going to do is actually go through those data sets and create the prompt that we want as part of the fine tuning. So for this particular case, what we're going to do is add a template, right, where there's the prompt, the question, and the title. And so what we actually want to do is give the prompt something that says generate a concise and engaging title for the following legal question on an internet forum. Title should be legally relevant, capture key aspects of the issue, and entice readers to learn more. And the prompt, the actual output that we get out of the model should be the title based on the question that we feed in. So this is a function that just tells it to do that, and it created these pre-processed .jsonls. So now all of them are in that format. As you can see, this is what they look like now. with the input and the output. You can see that there's essentially the prompt here, then the title, and then the output should be the following, which is the actual title itself. So now we're getting to the point where we are actually going to run the fine tuning using LoRA. So I'm just going to start this cell because it will take some time, and I'll explain a little about LoRA while this runs. So what LoRA is it stands for low rank adaptation. And in traditional fine tuning, what you would actually have to do is take those 8 billion parameters in the case of Llama 8B, but then there's Llama 70B or even 405B, and you would need to tune each of those parameters towards the use case that you're trying to do. That's ultimately what fine tuning is. You're changing the weights of the model to learn a new output or a new behavior based on the use case, based on the data that you're giving it. What LoRA is it's a PEFT technique, which stands for performance efficient fine tuning, parameter efficient fine tuning. And it allows you to fine tune essentially less variables. What's really cool about LoRA is that you can think of the matrix full of weights called W. And then when you're actually fine tuning it, there's another matrix of equal dimensions called delta W. And delta W represents the change that you're making to each of the weights in the actual matrix W. Well, low rank adaptation essentially postulates that that secondary delta W is actually of low rank. So we can represent it as the multiplication of two smaller matrices with much lower rank. And that way we can actually only train two smaller matrices, and that would represent the changes that have to be made as opposed to doing a full fine tune. What's equally and even more cool is that you get an adapter. The result of a LoRA is actually a LoRA adapter. So instead of getting a new set of model weights across the 8 billion, you just get this essentially matrix or a set of matrices that can be applied to the original matrix at any time. And so what we'll be doing at the end of this tutorial is NIMs actually support hot swapping in different LoRAs. So you could fine tune and have multiple different use cases. And at the time of inference, it'll hot swap in the LoRA adapter. That way you can basically have the original model, or in this case, this question and answer where it'll create a title of a law model. You could have a totally different version fine-tuned on Llama 3.1 8B that is taught to do something totally else. And you could, again, swap those in at the time of inference. So I'll skip ahead here. As you can see, we're running the jobs. So as part of this fine-tuning job, we have the max steps as 50. This will take some time to run because, again, we are fine-tuning. If you wanted to change the scheme that you're doing, Nemo supports a couple different parameter-efficient fine-tuning methods. For example, you could use p-tuning instead of LoRA. And as I was saying down here, we can actually see what type of models we have. So in this case, we'll name our new model Llama 3.1 8B Law Title Gen. That's the generating of the titles. But you can do the original model, or you can have a list of different LoRAs. So while this trains, this will take some time. We can actually see the training as it's going down here. Again, we need the 8180 gig because it is a large model and it has to fit in memory. And so that's why you need a powerful GPU, but Brev actually provides that GPU to you and exposes the notebook directly to your machine. So we're actually doing a fine tuning and we're going to deploy it using a NIM directly. I'm on my laptop right now and I'm able to do this, which I think is pretty cool. And I encourage you to follow along with this. The entire guide, I don't know exactly how long this will take, but I'll get back to you once the fine tuning has completed. So as you can see, we are still training here, but we see that the loss is essentially going down. This means that we are slowly teaching the model from its original state with all its existing weights to be better at our particular use case based on the data we provided of that type of prompt, to give a more informative answer to the type of question we're asking, which again is like, here's a law question on some kind of forum, generate a good title. And we have essentially what we want the title to look like. And then we have the model guess what it should look like. And then we can compare, and hopefully it's getting closer and closer to what we actually want the model to look like, so that when it's done, we can actually see how well it's doing by running inference on the Nemo framework. And then we'll perform some model accuracy tests using a pretty standard metric called Rouge, RUGE, which is used in a lot of academia and papers. Alrighty, we're back. We are done fine tuning. We now have a LoRA adapter, which should, when paired with the original Llama 3.1 8B Instruct model, can now perform the task we want, which is when we give it a question that looks like a law-related question from a forum, it'll give us the title that it thinks it should have. And so we can check to make sure that the checkpoint actually exists, which it does. And as a reminder, you could fine tune even a larger version like the Llama 3.1 70B, but you will need a much larger GPU, something like the 8X8100 or the 8X H100 GPU. Right now, we only have the 8X A100, or sorry, the single A100 80 gig. And so now what we want to do is we really want to see how we did, how good is our new adapter when paired with the model. And so we're going to just do a smaller part of the data set, and then we're going to be performing it on the test data set. And now what we're doing is we're performing inference on the test data set using our new LoRA adapter. So you can see the path to the pre-trained model here is the adapter, the LoRA adapter that we have, and we're using the base model as the Instruct Nemo. So what it's doing is it's essentially applying the adapter, which has all of those changes to the weights that would teach the model to do exactly what we want it, which is again is that law question and answer use case. And it's performing inference, which is essentially producing the titles of all of the questions themselves. And then what we can do is we can compare the actual true title, right? Because we know what the title should be. These are cases that we've curated, and compare it to what the model predicts they should be. Then we can perform some validation using something like the Rouge metric here, which we'll be able to do. So we're going to wait for this to perform inference on all of them. This is more for like staging inference or just generally checking how your model is done. This it's not intended to be production level inference. That comes later. That's when we actually would want to deploy it on the NIM, which is, again, we'll be doing that shortly. And that's what will give you that really, really fast inference speeds to where you could deploy that NIM in your own architecture, in your own, wherever you host your, GPUs, and you could deploy the NIM there with your adapter, and then you could have a production level inference with your fine-tuned version of a model that is comparable to all of the closed source models out there today that are cutting edge. Alrighty, we've performed inference using the Nemo framework on that small subset of our training data so that we can see how well we did. And again, we're going to take a look at some of the predictions so we can look at the first one. For example, this is what our model actually produced. So the input, again, is that prompt where we're telling it to come up with a specific title based on the question. The question looks like, oh, in order to be sued for a particular jurisdiction, say New York, blah, blah, blah. And the output that we got is what constitutes a company's minimal business presence in a jurisdiction. So that's what we got as the actual output, and the answer, the label, like the ground truth, so to speak, is what constitutes doing business in a jurisdiction. So pretty close, and we can actually see how close we are on all of these using the score like RUGE, which is split up into 4. It essentially checks the number of common words. So the 1 is going to be the words that show up in our predicted answer versus the ground truth. The 2 is 2-word pairs that show up in the predicted answer versus the ground truth, so on and so forth. L is the longest common subsequence. So we're just defining that function, and then we're actually going to run it on it. So as you can see, these are the responses here. So the response length from our model is like 12 or so, and the response, the standard deviation of the reference length, which again is the ground truth, is 11.26, relatively close. And we can see the scores here on how we actually did. And they are relatively close to, this was from another run to show basically what could have happened, and I think we got pretty close. So if we're happy with these results of the accuracy, and we think that now this model is fine-tuned on our particular use case, and we want to actually deploy it, and we want to deploy it to have really fast inference speeds, that's where NVIDIA NIM comes in. So we'll be using LoRA inference using NVIDIA NIM. So if you recall, at the beginning of this tutorial, we went and joined the NVIDIA Developer program to get that API key. I saved that API key here. So what you're going to do is you're going to place that in the cell here. And what this will actually do is it's going to pull down the NIM for the Llama 3.1 8B Instruct model. And then it's going to start running the NIM. It's actually going to run the server with the Inference Endpoint. So what we're doing is we're downloading the NIM. This will take some time as it not only downloads the NIM, but then also boots up the NIM and actually runs it with an endpoint for inference. And it'll be running on 8000, and we'll be able to then check the available LoRA models, which again, because we have created that LoRA model and we have it in the right directory, it'll see, hey, you've created this LoRA that's called the Llama 3.1 and 8B Instruct title gen, which is the model that we just fine-tuned. And it'll also show the default model, essentially the one that is released to the public that everyone has access to. And so we'll be able to compare the difference, and then we'll be able to run inference on it using the /completions endpoint. And then we can essentially test it using, again, another question and see what the title it produces. And so at the end of this, will have completed not only fine-tuning this cutting-edge model, but actually deploying it for inference in a solution that could be done very similarly for production. And if you're an enterprise, there is NVAIE, which you can even sign up for, to where you have support from NVIDIA to do such a thing. But if you want to develop on top of NIMs, if you're just the average developer, you now have access to that. Today, with the developer program, you can go get access to these NIMs, which are incredibly powerful. I highly suggest you do that. So I'll get back to you once this NIM is up and running. Alrighty, as you can see, the NIM has been started successfully, which means it's now ready to be pinged. That inference endpoint is ready. We're just going to import the necessary Python libraries to actually call it. And as you can see, we have a couple models that are ready for us. The base model, which is the Llama 3.1 8B Instruct, and then we have our other model, which includes it essentially is attaching the LoRA to the base model, which is that 8B law title gen model. All right, so now we can actually ping the endpoint and try it out using our model here. So again, we want to generate a concise and engaging title for the following legal question from an internet forum. This is the same prompt we were using before, and then we actually give it a question. In order to be sued in a particular jurisdiction, say New York, a company must have a minimal business presence in the jurisdiction. What constitutes such a presence? Suppose the company blah, 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 and we want to come up with a title that's relevant for this question. So if we run that, we actually get a response. And the response is requirement for a business presence in a jurisdiction for a company to be suggested to that jurisdiction's legal jurisdiction authority of the forums. So that's what it gave us. That's what it thinks the title should be for this particular question. So if we instead use the base model here, let's see if it would give us a different answer. So I'm just going to replace the model that we're using. So here's what the base model gives us. You see how it's way different. It includes a lot of new line characters, and in general, it's not tuned on our data. And so it's much longer, and it even adds some flavor text at the end. Like, this title is legally relevant as it particularly relates to minimum business. And so we train the model to go from this response to instead, and if I go back again and run it on our original one, to actually giving us the title. So this is running on the NIM. This is the fastest possible inference speeds you could probably get, and you're running it on the A100 GPU, but you could deploy it anywhere. It's hyper optimized down to the hardware it's running on. And so as part of this tutorial, we joined the NVIDIA Developer program. We got access to the NGC catalog so we could actually use the NIM. We fine-tuned the brand new Llama 3.1 8B Instruct model on our particular data use case, which is carefully curated data that was actually created using the Nemo framework. We fine-tuned it using LoRA, which is a parameter efficient fine-tuning method using the Nemo framework. And then we use that LoRA as part of an adapter to perform inference on an NVIDIA NIM with our adapted LoRA here. So I think this is super cool. You can follow along with everything I just did today. And at the end, once you're done, I highly recommend that you either stop or delete your Brev instance. And thank you so much for watching. If you are interested in more tutorials or you have questions about anything that was part of this, please leave them in the comments below. We love to interact with developers. We think it's one of the best ways to actually get feedback and implement new features on the BrevDev platform or otherwise. Thank you all so much for watching, and I hope to see you all in the next one.